Okay, good morning everyone. Welcome back. Let's get started. So last time we talked about ancillary services. These services are required for the contingency event. So we talked about how to obtain ancillary service, and also we will talk about buying ancillary service and selling ancillary service in chapter 6. That's the end of chapter 6. Okay. So you may remember that how should services be obtained? Two approaches: compulsory provision and market for ancillary services. Now, this means all the generators must provide ancillary service, but that may not be efficient from economic perspective. So we thought about a market for ancillary services. So yeah, compulsory provision, advantage and disadvantages of compulsory provision. Then so we talked about market for ancillary services, long-term contract and spot market. Of course, we have advantages and disadvantages for this. So, and also we talked about the system balancing when renewable generators exist, and also combined with demand response, we saw that when we introduce demand response, the system can be much more efficient. And the demand side provision of ancillary service is good because it can be fast, and there can be a lot of small scale demand response providers, and they can be aggregated together as a virtual power plant. So this is actually popular in these days. So we have advantage and opportunities of demand side provision. So then next question is, how much ancillary services should be bought? And you are users, you are the users of power system, and actually you need to buy this ancillary service, but system operator purchase this service instead of you to operate the power system in a reliable way. So services are used mostly for contingencies, and ability is more important than actual usage. So that's why they can get paid based on megawatt, not megawatt hour. Even though you do not deliver any energy, still just providing the capability and ability and possibility. Keep your power plant ready for injecting more power. When contingency happens, you still can get paid. Okay, so availability is more important than actual usage. So then our next question is, how much reserve do we need to have? By the way, Kyung-Young uploaded a document that explains the terminologies in Korea. So all the terminologies here are English, but you also need to get used to the Korean terminology. So please refer to the document. So reserve is called 예비력, 1차 예비력, 2차 예비력, etc. Okay. So how much reserve do we need to have? If we do not have enough services, then we cannot ensure the security of the system, and we cannot maintain the quality of the supply. But if we have too much services, of course, this operation is easy. But that means a lot of cost. And that cost is passed to the system users. That means the increase of the energy price. Okay, so having proper amount of ancillary services is important. So system operator must perform a cost-benefit analysis, balance value of services against their cost. And what is the value of this ancillary service? Improvement in security and service quality. But this is complicated procedure and requires probabilistic optimization problem. The contingency event is probabilistic event, so that's why this kind of probabilistic optimization is required. So it should give a financial incentive to the system operator to acquire the right amount of services at minimum cost. And next topic is about, okay, we have energy, megawatt hour, and we have reserve, megawatt, and we need to consider these things together. So that is called co-optimization. Okay, and so far, no, we mostly talked about energy market, and also so you can think, so we talked about the markets for ancillary service as well. So we have energy market, and also we have ancillary service market. Then, one can think we have a sequential market for energy, and market for first type of reserve, market for second type of reserve, etc. So 1차 예비력, 2차 예비력, etc. Okay, so that is called sequential market clearing. So market for fastest type of reserve first, and then market for slower type of reserve, and then energy market, etc. But so in this kind of sequential market, so you are a power system generator. So you have a power plant. So some portion of energy can be sold for energy market, but some portion of the capacity can be sold for reserve market. Okay, actually this is energy because megawatt, and they should be sustained for some predetermined time. Okay, so as a generator, you need to decide how much to sell to the energy market and how much to the reserve market. You need to decide that. So you bid for the fastest type of reserve, and then bid the slower type of reserve, and then go to energy market. That means unsuccessful bids are considered in subsequent markets. But this is not quite good, and it leads to other problems in gaming of rules. So the terminology gaming in power system economics is not a good terminology. I mean, it means something bad. We study game theory to study the strategic behaviors, but power system economics, when people saying about gaming, that mostly implies negative things. So anyway, so this is not good. That's why we need to co-optimize energy and reserve. And obviously, there are interactions between energy and reserve. Because providing reserve means providing less energy. Anyway, you have a generator, it generates output. But if some portion is reserved for contingency reserve, then the amount of energy you can sell to the energy market is reduced. So yeah, more expensive generators have to produce energy. Partly loaded generators that provide reserve operate less efficiently and may need compensation. So a centralized market needs simultaneous clearing of energy and reserve. So that is called co-optimization. And we must ensure that no participants is disadvantaged. So let's look at the example. And actually, we have several examples. And these examples are slightly tedious. But let me go through. Maybe you need to do your homework. So not tedious, simple. This is simple enough to understand. So we have 4 generating units, and each generating unit have its own marginal cost of energy, dollar per megawatt hour, 217, 20, 28. And the maximum power, we have some maximum power, 250, blah, blah, blah. And so this is the maximum power generation, and this is the maximum reserve power that is denoted by R. R means reserve, 예비력, okay? So for simplicity, we have constant marginal cost, and unit 2 and unit 3 can provide reserve, and unit 1 and unit 4 cannot provide reserve. And here, for simplicity, the minimum power generation requirement does not exist. and no startup cost for simplicity. So let's think about the ability to provide reserve. Unit 2. Unit 2, the maximum power is 230, but the maximum reserve is 160. And the reason is because what? Why? This is the maximum power of your generator. But why the maximum capacity of the reserve is 160? It's because the reserve is the time constraint. You need to supply some amount of power, energy, within like 10 minutes or something like that. But generators have a constraint called ramp rate. What is ramp rate? Even though my maximum capacity is 230, it takes time to start from 0 to reach 230. Okay, so that is called ramp rate. If the ramp rate of your generator is high, you can quickly goes up and reach the maximum capacity. Okay, so the reason why it is 160 is that to provide reserve, it has some time requirement, and because we have a ramp rate constraint, the maximum you can generate within this time limit is just 160. You see what I'm saying? Okay, so that's why we have, so this is the energy produced megawatt, reserve capacity megawatt. So the sum of these two is 230, the maximum capacity of this generator. But the reserve capacity is limited by 160. Okay, and so this is the operating curve you need to select. Some portion of your generator is used to sell energy. Some portion of your generator is used to sell reserve capacity. Okay. So after this point, the sum of these two is just 230. This is 70. So sum of these two is 230. Okay. So this is for unit 2. This is for unit 3. Again, it has the maximum reserve capacity 190, as stated here. And if the ramping rate is high enough, we can have this kind of curve. Okay. So we have some assumptions about the market. For simplicity, perfectly competitive, and generators submit bids for energy only. That means each generator is a cost function, mostly quadratic function, and they submit their bids, and the operator try to minimize the energy cost only. The bids for energy only. Okay. And so market system operator dispatches generation to meet the load at minimum cost. So this is the optimization problem, the minimization problem, while providing the reserve needed. So here, the constant reserve requirement, we have 250 megawatt of reserve. Okay, that amount of capacity is reserved, and load varies between 300 to 720 megawatt. So here in this optimization problem, we have 8 decision variables. The generating power of each generator denoted by P1, P2, P3, P4, and the amount of reserve R1, R2, R3, R4. Actually, the dimension here is all megawatt. Okay, so and the objective function is Yeah, 2, 17, 20, 28. It comes from this constant marginal cost. So that means That means cost function is linear, not quadratic here. Yeah, so we have cost function, and we only have a power term here, not reserve term. And the constraint is the load generation balance. Sum of power should be equal to demand. It varies. The air in this room is not quite good, as you see. And the minimum reserve constraint, that was 250. So greater than or equal to 250. And the limits on generating units, maximum capacity of each generator. These numbers come from here. Okay, and the limits on reserve capability of the generating units. Unit 2 and Unit 3, the maximum reserve capacity, 160 and 190, and 0, 0. And also, as a generator, the sum of the power and reserve should be less than the capacity. So 250, 230, 240, 250, P1 plus R1, P2 plus R2, etc. So these numbers come from, again, here. Okay, so we have this kind of constraints. All constraints are linear, and our objective function is also linear. So this is linear programming. So you can solve it. Actually, yeah, you can solve it. So yeah, linear programming problem, and we have 8 optimization variables. And because the demand can change, we have 3 regions for the range of demands. And this is the solution of linear programming. So the meaning of this is in this range, P1 generated at its maximum reserve, R1 is 0. P2 varies depending on the load. Right? So 120 difference, 120 difference, and the reserve is 0. When load increase like that, P1 operates at its maximum, 250, and P2 also operates at its maximum, right? No. Yeah, the reason is because, actually, right. So the reason is because this plus that is 230. So it operates at its maximum. But the actual power generation is this much. This is reserved for contingency event. And for additional demand, that should be covered by P3. It varies from 0 to 50. Yeah, range is, difference is 50. And again, this amount of reserve, power is reserved, not used. And for this range, yeah, operate at its maximum, operate at its maximum, operate at maximum. And the most expensive generator covers additional loads. Okay, so the most expensive reason here. So Lagrange multipliers of the constraints means the marginal cost of the generator. So load generation balance. From here, okay, yeah, the amount of generation, the sum of P should be equal to D. That determines energy price. But we also have a reserve requirement. The reserve requirement is R2 plus R3 should be at least 250 here. And that determines the price of reserve. So, yeah, before you solve this problem using your software, Ch6.Power or something like that, you can try to solve it by hand. And so again, we have 4 units, the marginal cost, the maximum capacity, and the maximum reserve. So let's see. Unit 1 is the cheapest one. So it produced 250 megawatt, obviously. And unit 2 and 3 are needed for reserve. Yeah. And the requirement for reserve is the sum of these two is at least 250. But R2 is less than or equal to 160 because of the ramp rate constraint. So from these two, you see that R3 should be at least 90. The sum of these two should be at least 250, but this is less than or equal to 160. So that should be greater than or equal to 90, right? So R3 is greater than or that, and P3, the maximum is that one. So 240 minus 90 is 150. So P3 is at most 150. This is another constraint. You see, we have another constraint like that. Actually, when you put all the information here to the linear programming solver, the solver implicitly knows that this is the constraint. Okay, and R3 should be less than 190, and from here and there, R2 should be greater than or equal to 60. So that minus that is 170. So maximum power is again limited by 170. So for three ranges of demands, range 1, range 2, and range 3, let's see one by one. Unit 1 produces, for this range, unit 1 produces 250. And then unit 2 is the marginal unit. As you see here, it varies its output power. So unit 2 is the marginal unit, and the production increases from 50 to 170 from this solution. And set the marginal price for energy at $17 because unit 2 is the marginal unit. So the marginal cost of unit 2 is the marginal cost of the system, the energy. And unit 2 and unit 3 provide more than enough reserve, so this constraint is not binding, and the price of reserve is 0 in this area. And in this range from 420 to 470, unit 2 is kept at 170 because it must provide 60 megawatt of reserve. So actually that is reflected here from the solution here. So unit 3 is the marginal unit. The production increases from 0 to 50. And it sets the marginal price for energy at $20 because the marginal cost of unit 3 is 20. And then let's think about the price of reserve. Price of reserve is the cost of additional megawatt of reserve beyond 250. So R2 plus R3 should be greater than or equal to 250. So when we compute the price of reserve, we need to compute the price, the marginal cost at this point. If we want to provide 1 megawatt more reserve, how much does it cost? That's the marginal cost of the reserve. And to provide 1 megawatt further, how can we do that? So unit 3 provides its maximum reserve 190 megawatt. So to get 1 more megawatt of reserve, unit 3 must reduce output of unit 2 and increase the output of unit 3 by 1 megawatt. This is for energy. So, yeah. Am I saying? To get 1 more megawatt of reserve, must reduce the output of. Yeah, so unit 2, the output of unit 2 is decreased by 1 megawatt, and that is compensated by unit 3. So, energy or power for energy selling, this amount is increased by 1. Do I say correctly? (2017). So the solution here is reserve 60 and 190. How can we increase 1 megawatt of reserve at a minimum cost? And we can do that. How? So reducing the generation of unit 3, 1 megawatt for energy delivery. So increase that energy here by 1 megawatt. And then we can increase 1 megawatt of reserve here by decreasing this by 1. Okay. Decreasing by 1, increasing by 1, so we can increase this by 1. Okay, so we can increasing the reserve capacity 1 megawatt. And what is the cost of doing that? So decreasing this minus 1, increasing this 1, no, $20 and $17. So minus 17 plus 20. So that costs $3. So that is the price of reserve here. Yeah, price of reserve in this case $3. And similarly, for another range, here, unit 4 is the marginal units. So increases the production from 0 to 250. Yeah, this variation is covered from here. And the price of energy is $28 because of the marginal cost of unit 4 is that. And the reserve constraints limit production of unit 2 and 3 at 170 and 50 respectively. What is it? So, so what it says is the reserve 60 and 190. So, so unit 2 can generate only up to 170 because maximum is 230. And what was that? 190. So, so maximum 50 megawatt of reserve. And to get 1 additional megawatt of reserve, what we need to do is reduce the output of 2 by 1 megawatt here. Increase the output of unit 4 1 megawatt. So check it yourself. Rather than decreasing this by 1 and increasing this by 1, decreasing this by 1 and increasing this by 1 is better. And so the decreased amount of energy is compensated by unit 4. So we have additional $28 of cost, and reducing this is 17. So the price of reserve is 28 minus 17, so $11. Same thing can happen by decreasing this by 1 and increasing this by 1 and increasing this by 1, but that in that case the cost is 28 minus 20, so $8. So why do we need to choose it?
유닛 3가 Rmax가 190인데 이미 190 리저브하고 있어서 그 다음 거.
Oh, good point. Thank you. You see what he said. So here the solution says, in this range, the R3 is 190. Okay, so the unit 3 cannot increase reserve anymore. So yeah, we cannot make it 191. So to increase the reserve capacity by 1, we need to increase this 1. So we need to decrease this by 1 and increase this by 1. Yeah, so the price of reserve is that, $11. So from all of this analysis, what you can get is when demand changes from 300 to 720, the energy price, this is the marginal cost of unit 2, marginal cost of unit 3, marginal cost of unit 4. This is the energy price. And the reserve price for range 1, 0. Range 2, what was that? Yeah, $3. So $3 and then $11. Okay? So from this, you can compute the profit of each generator in this market. So check the profitability of unit 2. Unit 2. Unit 2 is the marginal unit for energy. Here, in this range, the energy price is same to the marginal cost of the unit 2. So no profit. And the price of reserve is also 0, so no profit. And then for range 2, output of unit 2 is capped by reserve requirement. In unit 3 is marginal unit and energy price is 20, reserve price is 3, and the marginal cost of unit 2 is 17, as we know. So unit 2 gets its opportunity cost for every megawatt of reserve. Opportunity cost. Yeah, anyway, so unit 2, the marginal cost is this much, and the energy price is 20, and reserve price is that. So opportunity cost for every megawatt. What is the opportunity cost for every megawatt of reserve here? So to provide a reserve service, you need to sacrifice of selling this much. So it has opportunity cost of what? What is the opportunity cost here? So to provide reserve service, you need to sacrifice to provide energy service, and the energy service gives you $20 of benefit, right? And by selling a reserve service, you can get $3. So opportunity cost is $17. That is same to the marginal cost. Okay. So it is not penalized for providing reserve. Okay. And for the next range, in this range, unit 4 is the marginal unit. Energy price is $28. The profit, $11 for energy production. Okay. Energy price, the marginal cost, 28. We are talking about unit 2 only. So the unit 2 has the marginal cost $17. So 28 minus 17 is 11. So this is the profit. Profit is revenue minus cost. So profit is $11 per megawatt hour for energy production. And the reserve price, as we computed, that is $11. Again, revenue from reserve is equal to opportunity cost because unit 2 is marginal for reserve 2. Yeah. So unit 2 is, in this case, unit 2 is indifferent to producing energy or reserve because it gives the same profit. But unit 3 makes a profit on energy and reserve because it is a marginal for neither. So finally, this is the profitability of unit 2. Demand. This dashed line is the revenue from sales of reserve, and this is this revenue from sales of energy, and this is the total profit. Total profit means sales minus cost. Okay, so revenue, this revenue, that revenue minus cost. So this is the total profit. Looks good. You can get money by providing energy and reserve capacity. Any questions? Actually, I wanted to give you this assignment, but you don't need to do that. It looks like good for you.
질문이 있습니다. 그래서 유닛 2에 대해서만 얘기하고 있는데
오.
오퍼튜니티 코스트에 대해서 잘 이해를 못했습니다.
So yeah, opportunity cost here. In this case, the unit 2. Okay, when you have a generator, you can the output power. You can sell this output power for energy market or reserve market. Okay, so the opportunity cost means that when you sell it to the reserve market, you need to give up the benefit by selling to energy market, right? So here, when you are selling to the reserve market, there's $3. But if you had sold it to energy market, that is 20. You could have expected $20. So the cost is $17. Your opportunity cost is $17. And that is same to your marginal cost. Okay. Yeah, and similar analysis here. So maybe you can check the profitability of unit 1 and unit 4 and unit 3, something like this. You can get this kind of a graph. We have another example. Assume that the market rules allow units to bid separately for energy and reserve. In the previous example, the generators only bid for energy market. So that's why the objective function has the energy cost only. But here, the generator can bid both for energy and reserve. Okay, and bid for reserve may reflect loss of efficiency or additional maintenance requirements. And this is the result. Marginal cost of energy is same as before, but marginal cost of reserve is computed like that, 0.057. Okay? So we have this additional term. Same problem, but slightly modified objective function. So energy cost plus reserve cost here. Again, this is a linear programming problem. You can solve it using Ch6.Power. And this is the solution. For different range of the loads, we have a different output. Here we have 5 ranges. So, yeah. So for detailed discussions in the textbook. And the conclusion here is that co-optimization achieves cost minimization, fair treatment of generators, and satisfaction of security constraints. So you don't want to do this as your homework. Yes or no? Answer correctly. So answer carefully. You don't want to do this homework. Yes or no?
No.
No. You don't want to do that. Right?
Absolutely.
Okay. Yeah. This is not your homework. Another example. Okay, so far we considered the constraint of the maximum output power and the reserve constraint, but we can also include the network constraints, the capacity limits. So for that, we have two countries, again, Bulgaria and Moldavia. They are connected by a line, capacity 800 megawatt. So one generator and one load, another generator and wind power and another load. And so the price, again, competitive market here and competitive market here. So the price can be computed like that. The energy price at Bulgaria, energy price in Moldavia, that's a function of generating power and the reserve. Again, so this is energy price and this is the reserve price. We have this kind of a linear function for the price. And here what we want to do is minimization of the cost at Bulgaria and Moldavia. So yeah, the difference here is that from this cost function, power generation and reserve, so if you take the derivative of this, you can get this one, 10 plus this plus this. And we have additional term here, the coupling between the power, energy, and reserve. Okay, so PB times RB, PB times RB, here and there. So, by the way, is it a convex function or not? You should check. No, when you have this kind of optimization problem, obviously this is convex function, right? Because this is x plus y square, but this function is not convex. Okay, so convex function plus some multiplication and non-convex function can be a convex function. It may or may not, depending on this number. Okay, so you should not assume that this is obviously convex. That's not true. You need to check. Okay, because yeah, this function is not convex. Anyway, so I think the author carefully choose this coefficient so that these functions can be convex. So we have a cost function for Boldria and cost function for Sildavia. And the constraints here are actually, yeah, so convex objective function. And the Fe is the power flow from here to there. So generating power minus outgoing power flow is the local load. And generating power at Sildavia plus incoming power is the net load minus the renewable generation, is 1,000 megawatt. And this is reserve. Yeah, this is for power and this is for reserve. Again, this is for reserve. And so this is the amount of energy, and this is the amount of, okay, so this is the amount of power, and this is the amount of reserve, and they should be less than 800 due to this capacity limit. So this is an easy convex optimization problem. We have several constraints. So when you solve it, you can get the solution. And for the first case, the optimal operation when no transmission capacity is allocated to sharing of reserve. That means we just assume that no reserve capacity is provided from here to there. So this capacity is only for power, energy. So maybe I'm using confusing terminology. So power, energy, they are different, but just for this explanation, I wanted to discriminate reserve and energy, or reserve and power. Okay. Yeah, but after you solve it, the energy transfer is this much, and the reserve transfer is that much. Actually, this is the reserve. The power does not transmit from here to there. That is just reserved. Okay, and it can be provided when contingency happens. So optimal operation when the transmission capacity is optimally allocated, and this is the result. And you can do this by solving this easy convex optimization problem using Ch6.Power again. So yeah, and then this is the result. This is the cost per hour. In this example, we only focus on one time slot. So that's why I'm interchangeably used energy and power. Okay. So, and the transmission capacity allocated to energy. That means, in this case, energy reserve total. Transmission capacity allocated to energy. Reserve 0 total cost, energy cost, reserve cost, and total cost. And allocation of transmission capacity between energy and reserve. This part, transmission capacity allocated to energy. 0 means 0 capacity is allocated to energy. But how can that be possible? So you'd better do this on your own as a homework, okay? So yeah, just solve it using Ch6.Pi, and this x-axis is actually the when you solve it, this is just the optimal solution. But this plot says if you limit the allocation of energy, if you limit the transmission capacity allocated to energy from 0 to 800, the cost changes. You see the problem? So that means you need to put some kind of constraint like Fe is less than something, and that limit changes from 0 to 800. And then you can get similar graph, but this is suspicious because from this optimization solution, this is the optimal solution. Energy transfer is this much. So I think when the capacity allocate is this much, where is it? Yeah, roughly 700, then the minimum cost is achieved. And even if you allocate more than 700, the cost cannot decrease further. So it monotonically decreases. So check it on your own as a homework problem and submit by Monday. Okay. And yeah, this is the result. So this, check it also. And next, a few slides. So who should pay for reliability? Not all users value security and quality of service equally. For example, producers and consumers, you do not value much about the power system security. You are okay even if outage happens. But the semiconductor manufacturing company is not like that. Or irrigation load. What is irrigation? Irrigation. Pumping water and give it to some land. That's called irrigation. And so ideally, users who value reliability more should get more security and pay for it, like a semiconductor manufacturing company. But with current technology, it is not possible. And the system operator provides an average level of reliability to all users. That means it may not be called fair to all users. The users who are more concerned about power system outage should pay more for reliability service, ancillary service. Okay? So the cost of operational reliability is shared by all users on the basis of their energy consumption. Yeah. So sharing the cost of ancillary services on the basis of energy is not economically efficient, and some participants increase the need for services more than others. So these participants should pay a larger share of the cost to encourage them to change their behaviors. So allocating the cost of reserve to consumers who are concerned more about contingency events. Okay, so economically, that is better. And yeah, who should pay for reliability? Similarly, who should pay for reserve? Reserve prevents collapse of the system when there is a large imbalance between load and generation. And large imbalances usually occur because of failure of generating units or disconnection of the transmission line. And owner of large generating units that fail frequently should pay a larger portion of the cost of reserve. So, okay, why do we need to have reserve? Because there are some contingent events. For example, the failure of an old generator or a disconnection of the transmission line. But currently, we are imposing the same price penalty for all generators who provide reserve service. But that is to be ready for a failure of old generators. So one can say, hey, you are an old generator, you have a high probability of breakdown, then you should pay more for this reliability service, right? So that encouraged them to improve the reliability of their units, and in the long run reduce the need for reserve and reduce the overall cost of reserve. Okay. So today we talked about buying ancillary service perspective, and this is the last topic. So let me keep it for last lecture. Okay. Any questions?